here we have a little test rig that I've put together, and we've got a power supply here, which at the moment I've got set to 10 volts. So from these terminals we've got a potential difference of 10 volts from the negative to the positive. It's not doing anything at the moment, it's just a potential to do something. The PD, the potential difference of the terminals. Okay, and I've got the current meter here as well, which you may be able to see there. It's showing 0, nothing happening. We haven't connected anything up yet to a circuit. It's just literally sitting there waiting to do something. Okay, now at the same time I've got a couple of meters wired in. This one's a voltmeter. I've got it set to volts, and at the moment it's showing, if you can see that, 10.1 volts. Let's just say it's 10 volts. Okay, it's reasonably close to 10 volts, which ties in with the meter on the power pack, on the power supply. This meter here is measuring current. So, and this is in, at the moment it's displayed in amps. It says 0.0. So we've got a voltmeter here, and we've got a current meter here. And what's happening, the way I've got this wired up here, is I've got the voltmeter, and we're going to put it across a resistor. Now there's a resistor, and I'll try and get this in focus for you. My autofocus is not very good. Anyway, that's a power resistor. It's actually a wire wound resistor inside of there in a ceramic case. Okay, and on this resistor it has a number. Okay, and I'll read that out to you because I can't show it on the camera properly. And it's a 1 kilo ohm. So that's a 1 kilo ohm resistor rated at 5 watts. That's why it's big, because it's quite a chunky little resistor. It's designed to warm up basically. 5 watts worth of energy released from it. So that's a 1 kilo ohm. 1 kilo ohm meaning obviously 1,000 ohms. Okay. So that's our first value we can put into our formula. So if we come back down to here. So we've got our resistor. Okay, that's our resistor there, and it's 1 ohm. Did I say 1 ohm? No, I said 1 kilo ohm. That's K. So it's 1 kilo ohm, or 1,000 ohms. Okay, and one of the meters is connected across the resistor. This is what we're going to connect in a moment. That's a voltmeter. Okay, so we're going to have a 1 kilo ohm resistor. We're going to connect a voltmeter across it, but we're also going to connect in another meter measuring I. So we're going to measure the current. I'll write current on there just to make it clear. And volts. Okay, so we're going to measure the current flow. Remember, that's the actual flow of electrons in the circuit. And we're going to measure the voltage across, or the potential difference across the resistor. Okay, and we know what the resistance value is. That's R. So R equals, if you like, 1,000. Because it's 1,000 ohms, a kilo ohm. Okay, and we're going to put a voltage across the whole resistor. Okay, so we are going to connect a power supply of, let's say, 10 volts across it. Alright, so 10 volts from the power pack, showed you earlier. Measuring the voltage of it, just so we can do it accurately. That's false. And we're going to measure the current flow through the resistor all the way back round. So this is really the circuit here. Okay, this is the flow through the resistor, and we're measuring the voltage across the resistor. Okay, so that's what we're going to do. And from this, we should be able to figure out how much power is being generated from the current and the voltage. So let's give it a try anyway, in practical terms. Okay, so there's our 1,000 ohm resistor. We're going to put 10 volts across it. We're going to measure the current here in amps. Okay, and these are my two connectors. So let's just do that. Connect this up to the the power supply, and there you go. Now you'll notice the voltage hasn't changed, which is correct. We're using a regulated voltage supply. It's going to keep the voltage constant across the resistor. But now we're saying 10.2. That's actually in milliamps. So it's 10, basically 10 milliamps, yeah, roughly 10 milliamps. So we're measuring the current flowing through the resistor as 10 milliamps. I'll turn the scheme down and probably get it a little bit more accurate. Take the relative button off. There you go. It's 10.09. So that's closer. Okay. So in terms of that, what we can say is, we can say, well, what's the power? How much power is this actually dissipating in watts? Okay, let's figure it out. So we can say W equals I times V. Okay, so we know the current, it's 10 milliamps. We know the voltage, it's 10 volts. So let's figure it out. So I get my calculator. Here's my calculator. What for years. So let's just type that in. Now you got to remember that I is actually in milliamps, and we need that in amps. So it's 0.01 of an amp. Do you get that? 0.01 of an amp. That is actually 10 milliamps, which is what we're seeing on the meter. So it's 0.01, okay, multiplied by 10, because it's 10 volts. Remember that? 10 volt supply. Okay, which equals, and that says, I don't know if you can see that. Oh dear. It's 100 milliwatts. So that actually equals 100 milliwatts. Right. So that's how much power is being actually dissipated from the resistor. And you know, I don't actually have a meter here to measure the power. There isn't a power meter on the bench that I can actually measure that, what the power is. But we don't need to, because we've just figured it out. It's 100 milliwatts. And you might think, well, how much power is that? And it's not a lot. I mean, 100 milliwatts. I'm putting my hand on the resistor, and I'm being honest with you here. It's just barely warm. Barely warm. It's like basically room temperature, plus a tiny, maybe it's half a degree, something like that. So, you know, it's not a lot of power. It's not warming up, really. It is warming up, but you can hardly feel it. It's not doing much. Right, let's try another resistor. Let's try another one. Now, here's a bigger one. Now, this is a 22 ohm, okay? And I think that's probably about a 30 watt resistor or something of that size. So it should be able to take up to 30 watts. So that's a 22 ohm, which is a lot less than the 1000 ohm. So it's 1000 ohm. I'm going to reduce it down to a 22. Let's try that. Get the shot back so you can see the meters. Okay, let's take that one away. Okay, now then, let's connect this one up. Now this is 22 ohms. Change the scale on my meter. Okay, voltage is the same, correct? Remember, it's a constant voltage supply that we're using, so everything remains regulated at 10 volts across the resistor. But now we're saying 465.9, if you like, 465 milliamp. Okay, now I'll switch that off for a moment. Let's do the maths. So that's 465 milliamps that we just measured there on the current meter, multiplied by the voltage, which is 10. So let's get the old calculator out again. Do that again. Remember, 465 milliamps is actually 0.465 amps. Okay, 0.465 amp is the same as 465 milliamp. So we always talk in terms of unit, so that's what we use. We actually use 0.465 and then multiply that by the voltage, which is 10. And the answer is 4.65 watts. 4.65 watts. Okay, so now we've got 4.65 watts. Okay, so the first resistor had 100 milliwatts. Second resistor had 4.65 watts. I think you appreciate that's a lot more power. That's much bigger than that one. Okay, and in real world terms, 4.65 watts. Now we're getting to a situation where you should be able to sort of feel some heat. It's nothing compared to a bar fire that you would plug into the mains, which is 1,000 watts. It's not that much, but it's about, you know, a third of the way up for like a soldering iron, which could be 18 watts or 20 watts. So we're kind of getting towards, you know, a device that could produce actual heat that you can feel. So let's just see if that's true. I'll reconnect it. Let's reconnect the resistor here. And I'm holding the resistor in my hand. Being a bit careful. Just because I don't want to burn myself or anything. And remember, we've got 10 volts and we've got 465.7, if you like, milliamps flowing through the circuit, actual flow. And you know what? Yeah, that's warming up quite nicely. Now I can actually feel a definite temperature increase. It's actually quite nice because in my workshop today it's a bit cold and that's keeping my fingers warm. So we've made a little heater and it's basically dissipating, if you like, 4.65 thereabouts watts of energy released. And in this case, because it's a resistor, it's not a motor or anything, it's a resistor, it is generating heat that you can actually feel. It's quite warm. That's nice, that. Right, so let's go another step further then. I think you're getting the hang of this. So let's try something a bit more drastic. Right, now this is another resistor and it's not very big. This is a 5 watt resistor and it's a 4.7 ohm, okay, wire wound resistor. This is a 4.7 ohm. So 4.7 ohm, let's connect it up anyway. Let's do that. Right, now then, everything's overloading. My meter is going into cutout. It's more than 3 amps and my meter is overranging. It means it's more than, because it's more than 2 amps. So it's overranging, said OL, and you know what, that's getting red hot when I do that. That's getting really warm, and that was just after about a second, so I don't want to push it too hard. So that's obviously going to generate a lot more power. So you can see that the whole point of this is I'm trying to demonstrate is that as the resistance drops, as the resistance gets lower, the current through the resistor gets higher. You've seen it on the meter. Until I got to this one, it's actually overranging. It can't even measure it. It's off the scale. It's off the chart. And you generate more heat. So I hope that gives you a feel, if you like, an overall concept of power being radiated from, in this particular case, a resistor. And it's not just a case of, you know, the more voltage you put across it, the hotter it's going to get, although that's true. But it's also a case of the lower the resistance is, the more power you'll get as well, as long as the power supply can actually deliver the power that you're looking for, that you're trying to radiate. So there's a definite relationship, and it all comes down to what we're saying earlier with Ohm's Law, there's a definite relationship between, a clear relationship between voltage, current and resistance, and it's all summarized up in Ohm's Law, which you can also derive power from with Ohm's Law as well, from W equals I times V. So there you go. It all links basically. It's all interlinked, and depending on which Ohm's Law formula that you use, or if you transpose it to get the term out that you're looking for, if you wanted to find R, or if you want R, or if you wanted to find I in that particular formula, you could transpose it, then you'd end up with a different formula, and then you could use your calculator to figure that out. Or you could just go on the internet and download a chart where it's all being transposed for you. You don't have to do anything, just print it out and stick it on your wall or something like that. And then you can work all this stuff out using the correct formula. So that's basically a summary of the entire thing. And we've been looking at power, and we've been looking at how resistance affects power, and how, because of its current, and how the voltage across the resistor affects power as well. So there's a real correlation going on between the whole thing, and that's really what Ohm's Law is all about, being able to derive one from the other two, or the other three, or whatever. And I hope that's enough to explain, basically, and to get a sort of a general overview of what's going on. We've got electrons flowing in a copper conductor, and in real life, electrons actually flow from the negative terminal to the positive terminal. I'm talking actual electrons on a particle level. They actually travel from the negative terminal, or 0 in this case, to the positive terminal, 1 in this case. So the actual electrons would be going that way. But in engineering terms, we do it the other way, and there's a reason for that, which is complicated. And it's called conventional current flow, whereas it goes the other way. You actually go from the positive terminal to the negative terminal. So you'll see things like the flow of current. In electrical terms, we're talking about from positive to negative. But also in electrical terms, if you're talking about physics particles and actual electrons, in the real world, the actual electrons are moving from the negative to the positive. Yeah, it's confusing. And I wish they hadn't done that, because it makes life a bit complicated when you're talking about which direction the thing's moving in. There's a reason for it. It's basically because the actual particles do indeed move from the negative to the positive, but in a copper conductor, you've actually got, because you've got a displacement of an electron, it leaves a gap. Imagine like lots of ball bearings in a tube, and you take one out, take a ball bearing out of the tube, you've left a gap. Now if you keep doing that in a succession along the tube, you'll see that the gap moves in the opposite direction to what the actual electrons do going in the other direction. So yeah, it's a bit complicated, but that's what's going on. So in electrical engineering terms, we talk about the gap movement. We talk about the bit that's actually missing, and that's because it makes all the numbers positive, and you can do your maths without making everything negative all the time. You're not dealing with negative numbers all the time. You're actually dealing with positive numbers, which makes the formulas easier to work out. That's really the only reason why they do it that way. I wish they hadn't done that way. They should have just kept it as physical properties, but that's my opinion. Okay, so that's the overview of power, Ohm's Law, volts, current, resistance, you name it. And I hope that makes sense. If you've got any questions, post a comment, and we'll try and clear it up for you. Thanks for watching.